Can you see the screen?
Yes, sir.
Just coming in 1 minute. ಕ್ಲಾಸ್ ನಡೀತಾ ಇದೆ. So let me explain to you from where did this uniform boundedness principle actually came up. Okay. So let me take x and y to be non-linear spaces. X and y. Non-linear spaces, and take a sequence Tn in bounded linear operators from x to y. So let us recall a few things. These are useful tips, by the way. If T belongs to BLXY, bounded continuous linear operators, then norm of Tx is less than or equal to norm T into norm x. This is a very useful result. In particular, if f belongs to x star, that is this y is k, then mod fx is less than or equal to norm f into norm x. This was the question, sixth question. This is a very useful used frequently. Now, if suppose this Tn converges to T belonging to BLXY as n tends to infinity, then norm of Tn minus T will go to 0 as n goes to infinity. So for any x, norm of Tn x minus norm of Tx is less than or equal to norm Tn minus T into norm x. I'm using the linearity here. I'm using this part. This goes to 0 as n tends to infinity. Therefore, this sequence Tnx converges to Tx as n tends to infinity. This is called pointwise convergence. Okay. And this one is called norm convergence. Okay. Now, this gives you uniform convergence, all right. So it is also called uniform norm. So what it tells you is norm convergence implies pointwise convergence. Question is, will pointwise convergence implies norm convergence? This is the question. Answer to this is partial and it is from uniform boundedness principle. In general, no. Okay, answer is no. So what we are studying is whether point-wise convergence will be true for the. Now, if you look at this family F to be Tn, n equal to 1, 2, 3, etc. This is a countable family. Okay. But you can have F to be any family. Okay. That is the part of the uniform boundedness principle. It need not be countable. It can be anything. Okay. What it says is, if there is a point-wise convergence, then. So what you need is the base space X to be Banach. And Y need not be Banach. Y is just an harmonious space. Then it is true. Okay. This family case, when it is restricted to a sequence, it is called Banach-Steinhaus theorem. Those who want to go for PhD, this is normally if you say you know function analysis, they will ask you a question. At least state Banach-Steinhaus theorem. That's the reason why I'm trying to do this part. Okay. I am also doing something for you from the point of view of PhD interviews also. Okay. So before I proceed, you have any questions or remarks to make?
No, sir.
So no, drop now, you see, from 10 to 9. Sanu Kumar. Anyway, I don't know whether you want anything other than the course, some few things which will be useful for your life, if you are interested. Not more than 3, 4, 5 minutes. Outside the course, what is useful in your life? Would you like, Rishabh?
I don't know, sir, why others they leave the classes, sir.
No, that's okay. No, do you want something which will be useful for?
No, sir. This course is useful for me.
Not this course. Other than this course, do you want something which is useful for you in your life? You see, the issue is that life consists of of a person consists of 3 parts. One is the personal life. Second is the family life. Third is the academic life. Your academic life will end as soon as you finish studies. It could be BTech or MTech or PhD. Now, I have been going around for teaching the faculty members in many universities and other places. They told me, most of the people, they told me, we made a mistake of not learning when we were in the BTech classes. Now, what happens is after you finish your course and when you go back somewhere else, you won't get time to study at all. And second thing is, if you want to study uniform boundedness principle yourself, it will take about 5 to 6 hours. But a teacher can give you a ready-made material for you in 3 to 4 hours or even 2 hours. So you save about 5 to 6 hours time. Therefore, it will be very good in your own interest that you listen to the lectures. If you have problems, you can stop the teacher and ask for the explanation. Second thing which I want to tell you is there is somebody else who is paying for your stay, for your studies, etc. You have to be faithful to those people also. That is why I am saying I don't mind if you bunk a class. I'm not the loser, right? You are the loser. So I would like to tell you, don't lose yourself at this time of the age. This is exactly what Vivekananda said. Vivekananda ji said that if you want to commit a mistake, you are welcome to commit a mistake, but not a old one. Right? So that's about 3 minutes which I wanted to tell you. So if you want to commit a mistake, commit a new one. Don't commit a old one. If you have been bunking classes and you think it's a mistake, don't commit it again. And second thing is, don't advise your friends to attend the classes. Okay? When they have problems in their life, they will understand it is too late. It is just like reaching a railway station after the train has left. That is why I am saying it will be dangerous if you start bunking the classes. All right. So let me share I'll send you the whatever I have written yesterday and today to today. Okay. Can you see the screen?
Yes, sir.
Okay. So this is where we were yesterday. That we used the Bayes theorem somewhere here. Okay. Now this is what I was telling you. This family F here is a subset of BLXY. It need not be a sequence. It can be even uncountable also. All right. So yesterday we were using the Bayes theorem here, and so now you take E to be a bounded subset of X. Okay, I'm continuing from there. That is, NORM X is bounded by some alpha for all X in E. That's the meaning of boundedness. Consider X in E and F in F. Now, norm of F is a bounded linear operator. It's Rx over alpha plus A. Okay. So you look at this X, divide by Rx by alpha, and you add a A to it. Okay. Where did you get this A from? This A is here. Okay. There is some point A in X and some R such that UXA intersection DM. This A I am talking about. Okay. So this A here, and you look at Rx by alpha, and let us choose alpha, R later. Okay. R is positive. Now, norm of Fx is nothing but alpha by R into norm of Rx by A. This is what I was telling you. This alpha is positive, R is positive, so that mod will go. So what we have here is alpha by R. So to this you add minus A and a plus A. So F of Rx by alpha plus A minus F of A. Right? Now that is same thing as alpha by R remains the same thing. That is, you now use the triangular inequality. It is norm of Rx by alpha plus A plus norm of F of A. So this alpha by R is here. This is bounded by M. This is bounded by M by the choice of A and the X. So thus norm of supremum of F of X belonging to A is bounded by 2 alpha M by R. Therefore, that the family F is uniformly bounded. So that's what you have. The family actually is a bounded family on E. If we let E equal to closure of X of closure in X, with center at 0 and 1, then it follows that the supremum of this one, you continue, you use the previous result, then you get it will be supremum of f belonging to f is less than or equal to 2m over r. R is fixed, m is fixed, 2 is fixed. Therefore, this supremum of the norm is bounded. So that is the this you get a uniform bound on the element of this here, because this 2m and r, they are not anyway related to f at all. That completes the proof. So what it says is, the first remark, this result says either each f is on a bounded subset of Banach space into a fixed ball into the norm linear space y, or there is some x such that no ball in y contains fx with f in a. Actually, the following properties, only the following properties of f belong to are used. That x going to norm of fx is continuous and non-negative, and the norm of f plus y is less than or equal to norm of f. This is the only 2 points which you have used, nowhere else. And of course, norm of f of kx is something like norm of k into norm of fx. So only these properties are used. Therefore, this theorem can be also proved for a continuous seminorm. Okay. That's another comment which you say. Let me not worry about the seminar. Okay. Let x and y be non-linear spaces and f belong to Vs. Then x not be x in x such that f is bounded at x, which is a subspace. And suppose x naught is not x, then by the interior of x naught is empty. That is, a complement of x naught is dense in x. Thus, f is unbounded at some point x in x. Then f has to be unbounded at each point x. That is exactly what you use for the. Okay. Now, this is the theorem which I was trying to tell you, that x be a Banach space and y be a non-linear space, and Fn be a sequence in BLXY. In the theorem, we had not taken a sequence, we had taken a family. That I explained to you in the beginning of the class. Then the sequence Fnx converges in y for every x in x, then define fx equal to limit of n going to infinity of x. Okay. Banach-Steinhaus theorem. If f is a bounded linear map from x to y, that is, you take x to be a Banach space and y to be non-linear space, Fn be a sequence such that Fnx converges to. So this you are taking as a part of the hypothesis that Fnx converges in y for x belonging to, for every x belonging to x. Then you define an operator f to be the limit of Fnx. Okay, since you have taken for granted this one. Now what it says is, if you have given this hypothesis, then what it says is the norm of f is bounded by limit inferior of norm of Fn. That is the supremum of norm of Fn n equal to 1 to infinity. This middle part follows because of the uniform boundedness principle. If E is totally bounded, then Fx also converges. Okay. So proof, suppose alpha equal to supremum of Fn n equal to 1 to infinity. Now why should this exist? Because of the hypothesis here. Okay. Okay, let me see. All right. So let alpha be norm of Fn n equal to 1 to infinity. It's clear that f is linear. Okay, that's obvious. This f, whatever the fx equal to limit Fnx is clear. The set norm of Fnx n equal to 1 to infinity is bounded because Fnx is a convergent sequence. Why it's a convergent sequence? That's the hypothesis. Okay, Fnx converges for each x. Okay. So convergent sequence. So the set norm of Fn n equal to 1 to infinity is bounded by the uniform boundedness principle. Okay, that's what we had said. Okay, so norm of f of x is limit n going to infinity of norm of Fn x. That's the definition. That is less than or equal to limit inferior of Fn, etc. This limit inferior is bounded by alpha, and therefore norm of f of x will be bounded by alpha. So you take here norm x equal to 1 and take supremum, you get norm f. And that norm f will be bounded by limit inferior of this of norm Fn, that is given to be less than or equal to alpha. Therefore, this function f or this operator f is actually a bounded linear operator, therefore it is continuous. Okay. Now this is something to do with the compactness, so let's not worry about that totally boundedness. So again, we have some simple remark here. The hypothesis of the completeness of x cannot be dropped from the result. Okay. So that's what I was telling you. If you look at this theorem, uniform boundedness principle theorem 9.1, let x be a Banach space. Banach space means it's a complete nonlinear space. That you cannot drop. If you drop it, then the theorem may not hold. Okay, some remarks are wrong. The Banach-Steinhaus theorem here. Okay. So this is the, I'm talking about this again, some final remarks, 142 page. Okay. We make some remark. Hypothesis of completeness of x cannot be dropped from the result. For example, you take x equal to c naught naught with the supremum norm. That's L infinity norm. Now, do you remember c naught naught?
Yes, sir.
So that is the sequence space, okay, with finitely many elements which are non-zero. And that is going to be not a, it is not complete, because you can have a Cauchy sequence, it may not converge. You know this or not, you don't know. Should I have to do it for you?
Yes, sir.
C naught naught is not complete, you should know that. I'll share it. C naught naught is the set of all sequences only finitely many are non-zero. Okay. This C naught naught is part of L infinity. We have supremum norm here. For example, you take the sequence 1 by n. Okay. That is 1, half, 1/3, etc. 1 by n. This is the sequence. Now you look at the element, say xn equal to 1/2, 1/3, 1/4, 1/n, 0, 0, 0, 0. Okay, this belongs to C naught naught because these are all zeros after n. So this is true for n equal to 1 to infinity. Now this sequence xn converges to 0 as n tends to infinity. Okay, all right. So this sequence, when you look at this sequence, xn for large n, okay, this sequence will be, maybe this is a hopeless example, all right. Let me give you a different example. Let's take the sequence 1. Okay. Now, if you look at xn equal to 1, 1, 1, and then 0, n equal to 1 to infinity. This is in C naught naught. Okay. This sequence xn will converge to the element 1, 1, 1, right? In L infinity. But this sequence is not in L infinity. Sorry, not in C0, 0. Because infinitely many elements are non-zero. This also is okay, but this is slightly better. So you have a, so this, suppose you call this as, say this sequence as 1. Okay. Then this xn converges to 1 in L infinity norm. But 1, this sequence 1 is not in C naught naught because it has infinitely many non-zero elements. So a Cauchy, so since this sequence is convergent, this sequence will be Cauchy. This xn is Cauchy. Okay. And it's a Cauchy sequence not converging in C naught naught. Therefore, C naught naught is not complete. Is it clear?
Yes, sir.
Anybody would like me to explain this again? Feel free, yeah? C naught naught incomplete means what? Means there exists a Cauchy sequence in C naught naught, but not convergent. In C naught naught, it converges in L infinity, that is okay. It's in L infinity now. So the previous example says that this is not complete. Therefore, C naught naught with L infinity norm is not a Banach space. Clear?
Yes, sir.
This I could have done it earlier. But then when I come back here, you would have forgotten by that time. That's why I did not do it earlier. I am doing it at a time when actually I need it. Okay. So I'll share it again. Can you see it? Right. So the example what we are talking is that the hypothesis that this is again we make some remark. The hypothesis of completeness cannot be dropped. For example, you take x equal to C naught naught with supremum norm and define this. Those who are sitting in the class, please note, sometimes it is, people don't ask the proof of uniform boundedness principle because it's a little long, and secondly, you should know Bayes category theorem. Okay, so nobody asks the uniform boundedness principle as stated, but proof of Banach-Steinhaus they might ask. So if you don't want to ask a proof of the Banach-Steinhaus theorem or uniform boundedness principle, then they will ask some questions related to it. This sort of questions will be not normally asked. Hypothesis of X cannot be dropped from the uniform boundedness principle. Prove it. Then you have to give this example. That is why this example becomes very important as a, for you, for knowledge. For a teacher, it will be a very good example for asking in the exam. Take it. So let X be equal to C naught naught with a supremum norm. Supremum norm means L infinity norm. So define Fn x equal to summation I equal to 1 to n xj, and x belongs to j. It's a finite sum, therefore this sum will always exist. Then this Fn will belong to x prime. Why? X prime means x star, okay? So you take mod of Fnx, that will be bounded by the L infinity norm of that multiplied by n. Okay? So if you fix n, so this mod of Fnx will be less than or equal to L infinity norm of this xj. Are you understanding? Shall I explain?
Yes, sir.
Should I explain?
No, sir. It's fine.
It's fine. Good. So this will be bounded by for each n, right? So norm of Fn is actually n. That also.
Sir, please share the screen, sir. It's not visible.
1 minute. So what this it is a functional on x prime. He calls it as x prime, but we call it as x star, BLXK. In fact, you can show this. So you can take, for example, xj equal to 1, 1, 1. Then you can show that this norm of Fn is actually n. Okay, for all n equal to 1 to infinity. Since norm Fn equal to n for all n, norm of Fn will be unbounded. It will go to infinity as n goes to infinity. Fix x in each in x1. Then there is a mx such that xj is 0 for j greater than mx. This is where you use the fact that you are working on C00. Okay. So C00 is, it has finitely many non-zero elements. So after some stage, it will become, this sequence becomes 0. So if you take any x, there is some integer m, after which this sequence becomes 0. But that sequence, may change with x. Okay, for some x it can be 100, for another x it can be some 200. So this m will depend on this given x here. So that is why you put your mx here. So mod of Fnx is less than or equal to mx into norm infinity. That's obvious. So however, the norm of Fn n equal to 1 to infinity is unbounded, showing that this 9.1 cannot hold. Point-wise, it is convergent. Okay, this family, right? Point-wise, norm of mod Fnx is bounded for point-wise. But uniform boundedness principle says if this is true, then the sequence Fn has to be bounded. But it is not true because the sequence is unbounded. Why does it happen? It happens because of the fact that C naught naught is not a Banach space. Okay, very important example showing that you cannot drop the hypothesis. Okay. So also, this example can be continued. Suppose you have f naught x equal to summation j equal to 1 to 1 xj. Okay. And Fnx will be equal to f naught x for n greater than mx. Then fnx will go to f naught x. That's obvious thing. So f naught also belongs to x prime, as one can verify easily. So the theorem 9.2, the hypothesis, Banach-Steinhaus theorem is also not true. So both the Banach-Steinhaus theorem as well as the uniform boundariness principle, you cannot drop the fact. So that is the point which I thought I will tell you. Now there are some consequences of this particular result. If X is a non-linear space and E is a subset of X, then E is bounded in X if and only if f of E is bounded in K for all f prime in K. This is called the duality problem. Okay. Some people call it as a resonance theorem also. Okay. You see, in operations research, you would have studied what is called a dual problem. If you are not able to solve
Yes.
the problem, you solve the dual problem. The same way, if you want to show that E is bounded, it is sufficient to show that f of E is bounded in the dual. Okay. Let me tell you what it is. Just 1 minute. So you have a non-linear space X and it has a dual. It can be written as X prime. Some people write it as X prime, some people write it as X star. Don't worry about the notation. Suppose you take a set E. Okay. And suppose you want to show it is bounded. Then it is equivalent to showing that f of E is bounded for all f in X star. So this is the problem in the original space. To prove that this is bounded, it is sufficient to show that. So you work in the dual space. F of E is bounded, this one. So the boundedness of this E is proved through the X star. That's the dual. This is the original problem. If we are not able to do it in the original space, you go to the dual and then do that. But question is how this follows because of uniform boundedness principle. That's an application. Okay. All right. So that's what I wanted to tell you. This is the resonance theorem. They call it as a resonance theorem, but anyway, it's also called duality problem. So let X be a non-linear space and E be a subset of X. Then E is bounded in X if and only if f of E is bounded in K for each f in X prime. All right. Let X and Y be non-linear spaces such that f from X to Y is linear. Then f is continuous if and only if G composed f is continuous for every G. This is also true. Okay. Now let X and Y be non-linear spaces and F be a linear map from X to Y be linear. All right, proof. If E is bounded on X, then norm of X is bounded by alpha for X in E. Therefore, mod of Fx is less than or equal to norm of X at norm X F into alpha. Therefore, Fe is bounded. That's simple. That's what I told you in the beginning of the class. Suppose Fe is bounded for every K and for every F in that, then define J from X to X double prime. X double star. You remember problem number 6 in your examination. It's exactly J of X equal to Fx if X is an X and F is an X star. Then this Jx is a subset of the double dual BL X prime K. X prime is a Banach space because K is so for fixed F in X prime, Jx F equal to F is mod Fx X belong to E is bounded. Hence, by uniform boundedness principle, we see that norm Jx is X belong to E is bounded. But norm Jx is nothing but norm X. That is, this J is a isometry. Last time I explained to you. See, J is an isometry. Therefore, the set E is also bounded. So here, you don't need the Banach nature of X, but what you use the fact that the dual is a Banach space. Dual is a Banach space because BLXY is complete if the range space is complete. That I have done it earlier. Okay. So the second part is also simple, not a very difficult thing. And some comments are given here and there. Okay. One most useful result, which I may not be able to do, is the divergence of Fourier series. Okay. So I will state this theorem, but I won't bother to prove this. If you are interested, you read it up. I will send you the material. So let X be equal to X belonging to C minus pi and X pi equal to, this is the periodic stuff. This is supremum norm. X pi equal to X minus pi is the periodicity, all right? Then the Fourier series for every X in a dense subset of X converges to 0. Sorry, diverges at 0. Fourier series for every X in a dense subset of X, in a dense subset will be divergent at 0. So that's what the point is. It takes a bit of time, okay. So it may take an hour or hour and a half. But it's a very important result that you should know that the Fourier series may not be convergent pointwise, but it will converge in L2 sense. This also I explained to you earlier. Then there is another interesting application of the uniform boundedness principle, what is called quadrature formula. Quadrature formula is nothing but the applications of numerical integration. Okay. So uniform boundedness principle has a total applications in the numerical analysis. That is what is important here. Okay. So I am not going to do this because it's not part in your syllabus. It may take time. All right. So the next main theorem that we have to do is the what is called open mapping theorem and closed graph theorem. All right. So let me see whether I should do it from this book or from this book gives a very simple proof. Okay. Quadrature formula, I am not doing it. Okay. Matrix transformation and summability method, I will do it. It will be useful for the statistics and big data affair. I will do it after I finish the what is called the okay. So in the next lecture on Thursday, I'll give you some introduction to what is called the open mapping theorem and the closed graph theorem. It's closed graph and open mapping theorem. Okay, this is what I plan to do. Now this man, I don't know what he does. I would prefer to prove open mapping theorem and then a closed graph theorem. But Lemier's book does the other way around. He does the closed graph theorem first and then the open mapping theorem. So let me see what the book on dancers does it. Accordingly, I'll do it. The time is around 12:55 in my watch. So I'll stop here. On Thursday, you will have a quiz. I have already set the quiz. Weak convergence and strong convergence. The quiz will be conducted by, may not be Sonu Kumar because he is probably out of station, but he will arrange somebody else to come and conduct the quiz. So please assemble in that room, whatever the room it is, and that person who is going to conduct the quiz will give you 15 minutes time. I will send the quiz paper to him. They will give you the quiz there. Very simple quiz. Don't heat your mind. It can be done in 5 minutes. All right. And best wishes. Don't worry about other matter. Bye-bye. Sonu Kumar, tell her. Huh?
Yes, sir. Yes, sir.
I'll send the quiz paper to you.
Okay, sir. I will tell.
All right. Bye.
Okay, sir. Bye, sir.
Spelling out. Huh?